Hello, I'm Brain Rainey, and welcome to the Little Glider That Could. There are moments in history that will never be forgotten, whether it's William the Conqueror's victory at the Battle of Hastings, the moon landing, VE Day, or countless others. And today, you are going to be introduced to another one. I present to you Lil Glider. Welcome to a moment in history. But before we get to that, we need to rewind. Students were to build a glider made from materials provided at the beginning of the semester with the goal to fly it as far as possible. The requirements are that it must be hand-thrown, must fit in a 16 by 16 inch box, and must remain intact for the flight. I included an implicit requirement to use as little material as possible, and this was assumed from the box requirement. A successful glider will follow all of the requirements and fly at least 20 feet while also using as little material as possible. It turns out that this implicit requirement was incorrect. The initial designs. When first designing my glider, the three main options I considered were variations of wing shape. The three potential options were airfoil, ellipse, or rectangular. To compare the different options, I utilized NASA's foil sim. This simulation had a lot of important information, but the most important was the L to D ratio. I included the same angle of attack for all three of the simulations and compared the L to D ratio, which I learned in lecture is the most important. And based off this information, I chose to go with the plate/rectangular design because the airfoil was only slightly better, but will require a lot more material and be a lot more complicated to design. After doing a little bit more research, I discovered the Ash 30 Me and decided to base my entire glider off of it. I scaled everything down from 26.5 meters to 12-inch wingspan, and then scaled every other requirement and dimension off of it. Here is my practice model made out of a pencil and cardboard and Play-Doh. The original model tended to nosedive at around 12 feet, so some Play-Doh was removed to increase the stability and reduce needless weight. After this change was made, the glider was able to gain a foot or two for a maximum distance of 14 feet. However, this is not nearly enough, but the glider path was stable and always remained in a straight path, so that was a good sign. So, while this wasn't a perfect indication of the design, based off the very sketchy design, the test still yielded valuable information. Based on my test runs, I knew a few changes would need to be made just besides using balsa wood instead of a pencil and cardboard. To increase stability, I would add wingtips and perfect the center of gravity. I also planned on making sure that the wingtips did not dip down as they did in the past example, and instead were straight or had a dihedral. In the end, the center of gravity was fixed, but the wingtips were not added due to the difficulties of gluing such small pieces, and a dihedral was not able to be designed. Other changes included the back of the wing switched to be under the vertical wing instead of on top, and each of the horizontal wings becoming one piece instead of split into two pieces. After a couple test runs, everything was going great until tragedy. The wings snapped in half. I then had to go back and fix my AutoCAD design so that instead of it being two separate pieces, the wing would be one for both of them, as you can see here. And ba-bam, here is my final design for Little Glider. How beautiful it is. Glider analysis. As you can see here, the center of gravity is right in front of the wing, and the quarter cord is just a little bit farther up. And I also calculated the coefficient of lift and drag. The coefficient of lift is equal to 2 pi times alpha, where alpha is the angle of attack. And since it was nearly impossible for me to find out the actual angle of attack from the videos I recorded, I will assume 5 degrees since that's a good estimate, leading to a coefficient of lift of 0.548. For coefficient of drag, it's equal to coefficient of lift squared over pi AR E, where E is the efficiency factor and AR is the aspect ratio, which is equal to the span squared over the area. The area is found by taking these three individual sections I had and adding them together and multiplying it by 2. With all of this, and using an E-value of 0.7, which is the E-value for a rectangular wing, the coefficient of drag is equal to 0.0037. Now the coefficient, or the E-value could have been a little bit greater, but I just went with rectangular because that's the closest shape it was. Now to the moment that you've all been waiting for history to be made. Bam. 25 feet, the crowd goes wild. I ended up beating my two competitors and moving on to the second round. Second round, we're not going to talk about that. But afterwards, I tried a different technique where I would take a running start, called it the javelin approach, and I would throw the glider as hard as I could from above my head. And wow, 35 feet. Can you believe it? This was even better, and I kept on perfecting this until I eventually got to 55 feet after 7 runs. These positive results prove that the initial design and design iterations worked. I'm very proud of Lil Glider and everything he achieved. After all, it was a moment in history. Next time, I would scale up the glider to have a wingspan of 16 inches to maximize the distance and make the building easier. Thank you for watching my presentation, and I hope you enjoyed this moment in history.